Glad you waited till that started, Sam. So, all right, ladies and gentlemen, class recording has started. So there is now no way that I will tell you the word that Mr. Schover and I use. So, anyway.
People are gonna watch that. They're gonna be like,
What? What?
Who's really gonna watch this?
Come on.
I wanna watch it.
Vortex Lord. Actually, I'll show you an email that I got this morning. Actually, so not from Vortex Lord, but along those same lines. I'll show it to you at the end of the period. It's like incentive for us to get through this. Now there will be no questions or anything at all. Like, yeah, we got it. Yeah. So, all right. Starting off today, I would like you to turn to page 106 of your book. Page 106 of your book.
Shut up, Sam.
And on page 106, we are going to look at problem number 91. All right, so on page 106, number 91 says, you are driving through town at 12 meters per second when suddenly a ball rolls out in front of you. You apply the brakes and begin decelerating at 3.5 meters per second squared. Part A says, how far do you travel before stopping? And we are just going to end that problem there. We're going to get rid of part B and then part C as well. Not that they're not good parts, but we were going to get to other things. So, all right. So in answering this question, right, first thing we have to do is what?
What are we solving?
What are we solving for? Wargo, what are we solving for in this problem? What does part A ask you to solve for? How far you travel, right? That's what it wants to know. And if it's a how far thing, what
Delta
variable?
X.
Delta X. Well done, Wargo. Well done. All right, so that's our unknown in this problem. Okay? Other things we know to help us get to where we need to get to. Some other information that they have in this problem here for us.
12 meters per second.
Okay, 12 meters per second is going to be what, Sam?
Velocity?
Which one?
The initial
Okay,
velocity?
so it says you are driving, right,
Yeah.
at this speed. So that's going to be your initial velocity, right?
Yeah.
That's what you're doing at the beginning of this problem. What else? VF is going to be what, Warga?
0.
Because,
Stop.
okay,
Apply brakes.
you apply brakes, right? So that implies that eventually we're going to stop. Okay? Last bit of information there for us is what?
Acceleration.
The acceleration, right? Even though they call it deceleration, that's going to give us the acceleration value. Now, Wargo, you already told us that physically what is this car doing?
Stop it.
So we can assume that this velocity is positive. We generally call the direction we're traveling positive. It's just, So if we have a positive velocity but we're slowing down, what has to be true about this acceleration?
Negative.
It's got to be negative, right? Remember we talked yesterday that anytime we slow down, velocity and acceleration have to have different signs. Okay? Good there? So we said that in solving a kinematic equation problem, the magic number for pieces of information is 3, and we have our 3 pieces of information. So now it's a matter of going to our list of kinematic equations and finding the equation that has these 4 variables, the 3 that we know and the 1 that we don't. Okay? So you pull out your list of kinematic equations, or you look over on that, you look over on the plaque over there on the side of the board, or side of the wall over there. And you find that this equation has those 4 variables, right? So now it's just a matter of plugging things in that we know. We know that the final velocity is 0, so that goes in there. equals the initial velocity being 12, and that value gets squared. The 2 is just part of the formula. You can't change that. It just stays there. And then the acceleration value we established was negative 3.5 in this problem. And then the displacement is unknown, and that's what we're solving for. So, just to make sure we do this correctly, right? Take care of some multiplication and division stuff at the beginning. This is going to be 0. This is going to be 144. And then if we multiply 2 times negative 3.5, we end up with what? Negative 7, right? So then it's negative 7 times delta x, right? What's next? Just to make sure we're doing this properly. Subtract 144, right? Subtract 144 from both sides, right? And then you're going to do what? Divide by 7. So you end up, sorry, yes, that's important. Divide by negative 7, right? And then when you run that through your calculator, did you run it through your calculator, Sam?
Yeah.
What'd you end up with?
20.57142857.
That's close enough. So that's what our calculator gives us. So 2 things we got to talk about here. Okay? First, 3 significant digits in this number here, right? 2 significant digits in this number here. So we should probably round this calculator answer, right, to 21 meters. Okay? Good there? But then, maybe more importantly to our understanding of this situation, when you have negative 144 divided by negative 7, what do you end up with?
A positive.
You end up with 20.5714, but it's positive 20.5714, right? So that means that our displacement is positive, because even though we're slowing down, right, which direction are we still moving in? You're still moving in the positive direction, right? So even though this acceleration is negative, the displacement has to come out positive to indicate that we're still moving forward. Okay? Good there? If you haven't done so yet, or if you only did a few and not sure, right? On Tuesday's date, this past Tuesday, the 8th of October, there was a bunch of problems on the calendar, a bunch of kinematic equation problems. Now that we've done 3 or 4 in class, maybe the ones that you weren't quite sure about when you did them originally, or if you didn't do them originally, they're there for you. The answers, there for you as well. Okay, so now that we've done a couple more in class, you might feel a little more comfortable doing that. Good there? Okay, let's shift gears. Just like yesterday, a lot of the things that I'm going to show you today, I'm going to show you some pictures, we're going to talk about some things. It might go a little fast for you to write all of it down. Okay? I will post these slides up online when we're done. So if you feel like you missed something, or if you didn't quite get it, or if you want to go back and see the way that I wrote it, they will be there for you. Okay? Last unit, we talked about position versus time graphs. And we talked about, like, you know, the duh sort of answer that position versus time graphs tell us 2 things, right? What do they tell us? Time and position, right? So it tells us where and it tells us when, right? Where is this object at what time? And we said that we can use a position time graph. Like, this is one of the first position time graphs that we looked at, and we talked about these 2 swimmers, and we talked about how far swimmer number 1 goes, and where she is at this time, and where swimmer number 2 is in relation to number 1. So there was a lot of where and when, but we also said that we can get another piece of information from this graph. And what else could we tell from a position versus time graph?
Acceleration.
Not acceleration. That's a little bit harder.
velocity.
We can tell velocity, right? And how do we tell velocity on this graph?
Yeah.
It's the slope, right? That we can tell that swimmer number 1, with its slope like this, is going faster than swimmer number 2 with its slope like that. And we also then used that to come up with this equation, right? Where this equation tells us where something is at any specific time, as long as we know how fast it's going, right? So relating the location with the time and the velocity. Good there? And I could have given you a graph like this and said, describe the motion of the object. So let's take 30 seconds and talk about it with the person next to you, right? Based on this graph, describe the motion of this object, keeping in mind that this is a distance graph, right? Not a velocity graph. So 30 seconds, talk to the person next to you, describe the motion of this object. Go.
Starts moving forward for a little bit. And starts moving back to the reference point, the original point. Then he moves back away from it, then he stays constant. Is that 49? Is that distance away from the reference point?
Yeah, that would be distance away from the reference point. So we probably, because this is an old graph I got from somewhere else, but I would probably call this position. Okay, so yeah. All right. So somebody in a previous class came up with a good story that goes along with this graph that I will share with you. Okay. So a student in the class. Okay. Let's call him Dylan. No, just Dylan. So that's all we're gonna call him. So All right. Starts off sitting at his desk, right? What's he doing at his desk? He's at rest, right? Don't exactly know what he's doing while he's sitting there, but he's not moving, right? Okay. Let's hope it's studying. But I give a opportunity to come up to the board to answer a question, which I don't really do often, so it's not realistic for this class. So Dylan starts walking towards the board, but realizes that he forgot the paper on which he wrote the answer back at his desk. So he has to walk back to his desk. Okay? But he doesn't get there because he then remembered what the answer was anyway. So he heads back up to the board, where he then stands and writes the answer on the board. Okay? Is that good? All right, a couple of questions that go along with this. First, when he's walking up to the board the first time, what can we say about his motion? It is a positive velocity. What else can we say about it? It's a constant positive velocity, because what do we see about the slope during this section? It's the same, right? But how does it compare to his velocity when he walks up to the board the second time? Let me give you a help. Are you ready? Oh, no. Sorry. If I take this and move it there, right? Wizard. So these two lines, what would we say about these two lines mathematically? They're equal slopes, and we call that, they're parallel, right? So parallel lines on this position graph means that an object is moving with the same velocity. Okay? Good there? Second question. Watch this. Ready? Okay. When he walks back to his desk because he forgot, or he thought he forgot the paper back at his desk, or he forgot his paper back at his desk, what can we say about how quickly he walks back to his desk? Not as quickly, more slowly, right? Because what do we see about the slope of blue versus the slope of pink?
Not as steep.
Pink is a higher slope, meaning that would be a faster speed, right? A faster velocity, right? But in the opposite direction. Okay? Good there? We okay with that? All right. Now, let's take it. Now, these graphs were the kind of graphs that we would have talked about. I'm just going to put this back. These graphs are the kind of graphs we would have talked about in the last chapter, the last unit. Because in the last unit, all of our velocities were constant velocities. So all of our position time graphs were straight lines, because constant speed, right? But now we would encounter something like this. Like it says up at the top, describe the motion of the object. What is this object doing? It is gradually increasing,
Acceleration.
or it's gradually increasing its velocity, which means, Margo, if it's gradually increasing its velocity, what would we say about its acceleration?
It's uniform.
It's a uniform acceleration because it keeps increasing, right? The velocity keeps increasing, right? So, when we encounter curved lines on a position versus time graph, that indicates changing speed. How much does it change? Well, it depends on how much it curves. Are we familiar? Go ahead.
This is talking about, so this is kind of like defining the M10 using derivative, that's what it is.
Yep.
That's the ever slow.
Yep. Are we familiar from math class with the concept of a tangent line?
Yeah.
That's where it heads eventually. Not in this class, but okay. So a tangent line, right, is a line that hits the graph in one spot and one spot only. Does that sound familiar? Kind of, sort of, maybe? Good. This graph, this line only touches the graph right there and nowhere else. But this line only touches the graph here and nowhere else. Okay? On a curved position graph, the slope of the tangent line tells us the velocity at that moment. So, slope of, not at, of tangent line equals the velocity. So on this graph here, what do we see about the slope of blue versus the slope of red? Blue has a steeper slope, and therefore, how fast was this object going at that moment in time? Faster than it was at the beginning. Good there? Okay. Now let's take this picture. What's happening in this graph here?
Slowing down.
Slowing down. If we look at the tangent line at the beginning, it's a pretty steep slope. But if we look at that tangent line later on, right, not as steep. Eventually, that's the tangent line, right? What eventually happens to that object in the bottom picture? It stays at rest, right? Because it's a flat line. What's the slope of a horizontal line? 0. What's the velocity of that object? 0, at least at the green section, right? So in this case, the slope of the tangent line will tell us the velocity, right? Calculus-wise, if you guys, when you get to calculus, if you do, whatever, okay? The slope of the tangent line is equal to the derivative of that function. So the derivative of that function gives you the derivative of the position function gives you the velocity of that object.
Would it be n tan times the point?
You would like, so here, let's do this.
Yeah.
Okay, so, oh, too far. What we find out is, oh, go ahead. What we find out is this equation right here is another equation that tells us where an object is. It still tells us the final position. But now, it not only takes into account how fast the object is going and for how long it's going that fast, but it also takes into account the acceleration of that value. And for how long it is accelerating. So not only does it tell us where something is in relation to how fast it's going, now it also starts relating that acceleration concept, or how much is it changing how fast it's going, because that plays an important part in how far it is. So Alex, this function, if we take the derivative with respect to t, that will give you the function for the velocity, and then you would just sub in whatever value for t you would want to know, and you could find out what the velocity is at any particular moment in time. All right, good there? Hold on a second. What? This one's pretty simple, though. I mean, this one's pretty easy. We're not going to do derivatives in this class, by the way. So if you have no idea what we're talking about now, don't worry about it. Good, don't worry about it. So. All right, let's take an example of this, and this example looks like this. Okay, so a speeder. I hate speeders. Travels at 18.2 meters per second. The instant that that speeder passes a parked police car, ooh, unlucky, the police begin their pursuit. The speeder maintains a constant velocity, and the police car has an acceleration of 4.50 meters per second squared. So the question asks us to show that the police car catches up with the speeder after 8.09 seconds, and to determine the location where this occurs. So before we do that, I would like you to draw me a sketch of what the position versus time graphs would look like for this speeder and this police car. What would the position versus time graphs for the red car and the blue car look like? Just a sketch. Think about what it tells you about the red car, what it tells you about the blue car. So this is an example problem from your book, so I'll tell you what page it's on after we're done so you can see it, in its entirety. All right, are we ready? Have you lived in suspense long enough? There it is. All right. What does it tell us about the speeding car in the problem? constant velocity, right? Maintaining a constant velocity, meaning that its position time graph should be a straight line. Slope tells us velocity. But what is it telling us about the police car? Acceleration, right? Meaning that its velocity is increasing, so the slope is going to increase. That didn't work as well as I wanted it to. All right, good there. Now, let's go about answering this question, right? Show that the police car catches up with the speeder after 8.09 seconds. What that's really saying there is 8.09 seconds is the answer. Show me that that's the answer. So we're going to use these equations that I just introduced to you. So there's the equation for the speeding car. Sorry. There's the equation for the speeding car. But what does it tell us that the speeding car is doing? Maintaining a constant velocity. If something is maintaining a constant velocity, what is its acceleration? 0. Because acceleration tells us the change in velocity. So, in that part of the equation where A was, now it's 0. V initial, right? Do we know what V initial is? Yeah, it tells us that that speeder is traveling at 18.2. So, where V initial is, now we go 18.2. And because it's saying that the car passes the police car, and at that moment the police car takes off, we're going to say that they start right at the reference point. So that's why that becomes 0. Okay? Good there? Where I got those numbers from? For the police car, there's the general equation, right? What was the police car doing when the speeding car passed him? He was parked, right? A parked police car, meaning that his initial velocity was 0. They both started at the same spot, so they both have the same initial position. But now it tells us constant acceleration of 4.5. So I plug that in here, right? And I multiply it by, I plug in 4.5 in for that spot A, but then I'm going to do what to it? Divide by 2 or multiply by a half, and that gets us here. Good there? Everybody follow how we went from the general equations to the specific equations for each car. Okay, police car catching up with the speeder, what does that mean? If the police car catches the speeder, how do I know when the police car catches the speeder? They meet, meaning that, Jamie, they have to be where? The same place, when?
At the same time.
Right? So, that means that this and this have to be the same. And if that and that are the same, guess what we can do to those two equations?
Make them equal.
Make them equal to one another. 18.2t equals 2.25 t squared. And now guess what? How many unknowns do we have in that equation? Just one, right? Just t. So, mathematically, right, we can divide this side by t and those t's cancel. Now we divide this side by t, this t cancels, but only one of those t's cancel, right? And now we're left with 18.2 equals 2.25t. And I think you guys could probably handle that one. And when you solve that for t, guess what you get? 8.09 seconds. And then if we wanted to determine the location, whoa, determine the location, what would we do? Take that t and plug it back into the equation. Which equation? Doesn't matter. Guess what you find out for xf? 147 meters. Alright, good there? So, for this weekend, a couple of pages from your book to read, and then a couple of problems that are similar to stuff that we talked about in class today. Answers to those problems are posted here online.